بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. In this video, I'll talk about linear programming problems. I'll change some word problems to a linear programming problem. So we will have word problems like this, and we want to write a linear programming problem. We want to change the word problem to a linear programming problem, and then to solve it either using Excel or whatever methods we learned. So these are the steps. You need to read the problem carefully and to identify the decision variables. The decision variables are the unknowns in the problem. What are the unknowns in the problem? These will be the decision variables, X, Y, Z, W. And then after you write the decision variables and know them, you use them to write the objective function, Z equals to whatever, or f of X, Y equals. And then you formulate the constraints of the problem. So let us start with example 1. The solar technology company manufactures 3 different types of hand calculators and classifies them as scientific, business, and graphing calculators. So these are the 3 different types. And classifies them to their calculating capabilities. The 3 types have production requirements given by the following table. So here we have electronic circuit components, and the scientific calculator needs 5 of them, the business needs 7 of them, and so on. And here is the assembly time in hours. The graphing calculator needs 4 hours, scientific needs 1 hour. And for cases, we put each calculator in a case, so each one of them needs 1 case. Now the firm has monthly limit of 90,000 circuit components. So these circuit components are limited to 30,000, to 90,000, and 30,000 hours of labor. So the assembly time is limited to 30 hours of labor, and we have only 9,000 cases. And this is the profit. If the profit is $12 for each scientific, 26 for each business, 40 for each graphing. And now here comes the question: how many of each should be produced? So this is the question. How many of each should be produced? And this will give you the decision variables. So he is asking about how many of each should be produced. So how many do we have? Each what? Each type. How many types are there? 3 types. So I will have X, Y, and Z. So what would be X? It would be number of scientific calculators. Okay. Scientific calculators. Y, the other variable, would be number of business calculator. Okay. And Z, the third variable, would be number of graphing calculators. So from this sentence, how many of each should be produced? I have X, Y, and Z. Number of scientific calculators produced. Y, number of business calculators produced. And also Z, number of business calculators, number of graphing calculators produced. So I finished from the first step. The unknown in the problem give me X, Y, and Z. Now write the objective function. Well, the objective function is maximize or minimize. So continue the sentence. How many of each should be produced to yield the maximum profit? So this is the thing we need to maximize. We need to maximize the profit function. I'll call it P. And now I need to write the objective function, the profit function. From where do I have the profits? You remember here he said the profit is $12 for each scientific. So if we produce one scientific calculator, the profit will be $12. What if we produce X scientific calculators? For example, X could be 100, could be 200. So what would be the profit for the scientific calculators? It would be 12 times X. And the profit for business calculators, 26 per each one. And the number we have Y. And for the graphing calculators, the profit for each one is 40. And the number of all graphing calculators is Z produced. So if I multiply 12 times X plus 26 times Y plus 40 times Z, I will get the profit, and I need to maximize this profit. And now the constraints, the third step, formulate the constraints. So subject to, and I put the constraints. Now, where are the constraints? I have 3 constraints, one for circuit components. I know that the number of circuit components are limited to 90,000. And each scientific needs 5, each business needs 7, each graphing needs 10. So the number of scientific, the number of circuit components would be 5 for each scientific times the number of scientific calculators plus 7 for each business calculator times the number of business calculators plus 10 for each graphing times Z, the number of graphing calculators. So if I have, for example, X 10, Y 20, Z 30, for example, then you can find the number of circuit components by multiplying 5 times 10 plus 7 times 20 plus 10 times 30. Now this number should be less than or equal to 90,000 because we only have 90,000 circuit components. So this is the first constraint. Also the second constraint regarding the assembly time. The scientific calculator, a scientific needs 1 hour. So if I multiply 1 times X, the number of all scientific calculators, plus 3 times Y, the number of all business calculators, 4 times Z, which is the number of all graphing calculators, I'll have all the assembly time, hours, then all the hours used in production. So this should be less than or equal to 30,000 hours of labor because I don't have more than that. And I have 9,000 cases, and there is a case for each one. So X number of scientific calculators plus Y plus Z. These are the number of all calculators produced. It should be less than or equal to 9,000, which is the number of cases I have. So we formulated the linear programming problem. We changed the word problem into a linear programming problem like this. You can put it in Excel and solve it easily. The second question. At one of its factories, a manufacturer of televisions makes one or more of 4 models of HD units without cases. So we have 4 models, 20N LCD, 42 inches, 42 inches plasma, 50 inches plasma, four types. 4 types of 4 models of televisions. Okay, 4 models of televisions. The assembly and testing time requirements for each model are shown in the following. So this model uses 7 hours of assembly time and so on. And test time, they also test after assembly. So 42 inches plasma takes 4 time to test and so on. And this is the profit for each type, each model. Okay. Together with the maximum amounts of time available per week. This is the total available hours per week, 2,000 for assembly time and 500 for testing time. So this is the maximum time they have, the limitation. This will help you writing the constraints. In addition to these constraints, so he told you that these are from here, you find the constraints. The supplier of cases indicated that it would supply no more than 200 cases per week. So the number of cases would be 200 cases. They need a case for each one of them. No more per week. And that of these, no more than 40 could be for the 20 inches LCD model. So the first model, 20 inches LCD, has only 40 cases, okay? So we shouldn't produce more than 40 of this model because we have only 40 cases. Use the profit, this is the profit, for each television shown in the table to find. Yes, now we need to find what? The number of completed models of each type that should be produced. This will give you the unknowns, the decision variables, okay? So how many types are there? We have 4 types. So X would be number of 20-inch, the first model, 20-inch LCD model produced. Okay, Y would be number of 42-inch LCD produced. Z would be number of 42-inch plasma produced model. And W would be number of 50-inch plasma produced. These are the 4 unknowns. To obtain what? The maximum profit for the week. So to obtain the maximum profit, so this is the function we need to maximize. So maximize the profits. And we need to write the objective function, which is the profit. Okay, the profit comes from where? From here. $46 for the first model. So if I want to find the profit from producing or selling all of these models, I multiply the profit for the number of this model produced, which is X. So 46 times X, 60 times Y, 75 times Z, 100 times W will give you the profit. And now subject to the last step, the constraints. The first inequality, the assembly time. 7 times X, 10 times Y, 12 times Z, 15 times W. This is the assembly time for all models. It shouldn't exceed 2,000 hours. The second constraint about the testing time, 2, 2, 4, 5. So 2x, 2y, 4z, 4w should be, or 5w should be less than or equal to 500. This is the 2 constraints. And then we know that the number of cases should be less than 200 or equal to. So how to get the number of cases? We add X plus Y plus Z plus W, because each model needs a case. And we know also that we have only no more than 40 for the first model, which is X. So I know that X shouldn't be greater than 40. So it's less than or equal to 40. So here is the linear programming problem for this question. Another example. A woman has a building with 26 one-bedroom apartments, 42 bedrooms apartments, 63 bedroom apartments available to rent to students. She has set the rent at $500 per month for one bedroom and 800 for two bedrooms, 1,150 per month for three bedroom units. She must rent to one student per bedroom. This is important. So only one student will rent the bedroom per bedroom. So even though here we have two bedroom apartments, one student will rent this room. Also three bedroom apartments, one student per bedroom. Okay, here we have three bedrooms, so there will be three students. Okay, and zoning laws limits here to at most 250 students in the building. So this is the number of all students she can rent to in the building, 250, not more than that. There are enough students available to rent all the apartments, okay, but one student per bedroom. So some apartments will take one student, some will take two, some will take three, according to the number of bedrooms. The question, and here the question in which enables me to write the variables, how many of each type of apartments? Okay, what are the types of apartments are there? This will give you X and Y and Z. So how many types? We have three types. So what would be X, number of apartments, or let me say number of one bedroom apartments. Okay, Y, number of two bedroom apartments. Z would be number of three bedroom apartments. So this is very important. This always the question will give you the decision variables X, Y, and Z to maximize her revenue. So this is the function we need to maximize. And here I can write the objective function. Maximize the revenue. Okay, what is the revenue? $500 per month for one bedroom units. So X number of all one bedrooms. So if I multiply 500 times X, this would be the profit from renting the the one bedroom apartments. And also 800 for two bedroom apartments and 1,150 for three bedroom apartments. So this will give us the revenue. And now we try to find the constraints. Now, they say she must rent to one student per bedroom. They mean per bedroom apartment, okay? They mean per bedroom apartment. So we have 26 one bedroom apartments. So she can't rent these 26 one bedroom apartments for more than 26 students. So X should be here less than or equal to 26. and the number of 2-bedroom apartments is 40. So she cannot rent them to more than 40 students. So this is really what we mean, 1 bedroom per bedroom apartment, okay, per bedroom apartment. So also Z is less than or equal to 60. So these are the 3 constraints. We have also here 250. What is 250? Zoning laws limit her at most 250 students. So number of bedrooms, 1 bedrooms, X, if you add X plus Y plus Z, you will get the number of the students, because 1 student per room. So the total number of students shouldn't exceed 250. And now we have the linear programming problem. Only pay attention to this sentence. Okay, I think I did not understand it carefully first, but now 1 student per bedroom apartment, this is what we mean, or what the question meant. Another question, 46. A company manufactures desks and computer tables. So desks and computer tables at plants in Texas and Louisiana. So there are 2 plants, okay? 1 in Texas and 1 in Louisiana, and each plant manufactures desks and computer tables, sorry. At the Texas plant, production costs are, these are the costs for the desk and for the computer table at Texas plant. And the plants can produce at most 120 units per day, units. So units, he did not say disks or both. The sum of disks and tables shouldn't exceed 120 units. At the Louisiana plant, costs are 42 for each disk and 57 for computer table, and the plant can produce at most 150 units. So shouldn't exceed 150 units. The company gets a rush order for 130 disks and 130 computer tables. So now the company gets an order of this. Somebody wants to buy this number of disks. So we need to manufacture 130 disks and 130 computer tables at a time, when the Texas plant is further limited. So there is also a limitation for Texas plants by the fact that the number of computer tables it produces must be at least 10 more than the number of disks. So this is also a constraint about Texas plant. And here comes the question. How should production be scheduled at each location to fill the order at minimum cost? So how should production be scheduled at each location? How many locations are there? There are 2 locations, Texas and Louisiana, but in each location, 2 things to manufacture. So production contains 4 different things. So I'll call X, for example, number of disks at Texas, okay, at Texas. And Y, number of computer tables at Texas, okay. And then Z, I'll call Z the number of disks at Louisiana, okay, and W, number of computer tables at Louisiana. So now I have my decision variables X, Y, Z, and W. I need to write the objective function. We need to minimize the cost at minimum cost. So minimize cost function. And the cost should become should depend on these 4 variables? Well, he said in the beginning that the production costs are 36 for each discs in Texas. So 30, if I multiply 36 times the number of discs from Texas, okay, plus 60 for each computer table. For Louisiana, 42 for discs. It's 57 per computer table, and the number of all computer tables from Louisiana are W. So 57 times W. So this will give us the minimum. This is the objective function. And now let us go to the constraint subjects too. What are the constraints? The production in Texas cannot produce more than 120 units. So X plus Y shouldn't exceed 120 units. Also, at Louisiana, a plant can produce at most 150 units. So in Louisiana, Z and W will give you a number of units. This shouldn't exceed 150 units. Okay, what else? Also in Texas, here the company gets a rush order for 130 discs. So we need 130 discs, okay? So the number of discs should be at least 130. So X number of discs in Texas, Z number of discs in Louisiana, we should get at least 130. So greater than or equal to 130, because we need, there is an order of 130 discs and 130 computer tables. So Y plus W should be also greater than or equal to 130. Still here, a limitation for Texas computer tables it produce. So this is what Texas, this is Y, should be, must be at least 10 more the number of discs. So X plus 10, okay, X plus 10. So Y should be at least X plus 10. So it should be X plus 10 or more. So it should be greater than or equal to X plus 10. So this is the constraint. Y should be greater than or equal to X plus 10. If you want to write it like this, I can take X to the left-hand side and write it as negative X plus Y should be greater than or equal to 10. And this is the problem. We can put it in Excel and find the solution. The last question would be this example, example 2. 2 chemical plants, one at Macon and one at Jonesboro, produce 3 types of fertilizer: low phosphorus, medium phosphorus, high phosphorus. So we have 2 chemical plants, and each one of them produce 3 types of fertilizers. At each plant, the fertilizer is produced in a single production run. So the 3 types are produced in fixed proportion. Okay. So the fertilizer is produced in a single production run. The Macon plant produces 1 ton of LP, 2 tons of MP, and 3 tons of HP in a single operation. So in a single operation, this is the production of Macon plant, and charge 600,000 for what is produced in one operation. So these $600 for one operation, and one operation will give you 1 ton of LB, 2 tons, and 3 tons of HP. On the other hand, one operation of the Jonesboro plant produces 1 ton of LP, 5 tons of MP, and 1 ton of HB, and it charges $1,000 for what it produces in one operation. I cannot determine the decision variables according to the previous information here. I have to wait to listen to the question, okay, what are the unknowns? If a customer needs 100 tons of LB, this is what we need to produce. And that's the question. How many production runs should be ordered from each plant to minimize the cost? So what is the question? How many production runs? How many production runs are there? There are only 2 production runs, one in Macon and one in Jonesboro. So X would be number of production runs in Macon plant, and Y would be number of production runs in Jonesboro. Oh, okay. Please read the questions again carefully and notice that you only determine X, Y, and Z, call the unknowns X, Y, and Z. Okay, so here he said how many production runs, and we have only 2 types of production runs. Now, what is the next step? Always follow the steps. I need to write the objective function. What do we need to do? We need to minimize or maximize? I need to minimize the cost. So what is the cost? Where is the cost? See, the cost, single operation in Macon charges $600. How many operations in Macons? We call them X. So if I multiply 600 times X, I will get the cost of producing from Macons. And $1,000 for each production run in Jonesboro. So this would be the cost function. And now, subject to, what are the constraints? Well, a single production run has we need what? Yeah, a single production run differs from the 2 plants. But what do we need? The customer needs 100 tons of LB. So I should produce 100 tons of LP at least. From where can I get the 100 tons of LP? Either from Macon or from Jonesboro. So from Macon, a single operation will give you 1 ton of LP. So 1 times X, which is the number of operations, this will give you the number of 1 ton, okay, plus. Now, how can I get the number of 1 ton from Jonesboro? Also 1 ton of LB from Jonesboro. So if I multiply 1 times Y, which is the number of production runs in Jonesboro, if I add these production runs, I will get the number of 1 tons. I need 100 tons of LP, okay? So X plus Y should be less than or equal to 100. Not less than, greater than, because at least I need 100. No problem to produce more because I need to give the customer what he wants. Okay, from MP, I need how many MPs? I need 260 MPs, 260 tons. Well, 2 from Macon. So if I multiply 2 times X, 5 from Jonesboro. So if I multiply 5 times y, this will give me all the MP can produce. This should be greater than or equal to 260 because this is what I need. I need 260 tons at least of MP, 180 tons of HP, and 3 tons from Macon from HP, so 3 times X, and 1 ton of HB and Jonesboro, so 1 times Y is Y, should be greater than or equal to the number of HP I need. I need 180 tons, greater than or equal. So this is the problem written in as a linear programming problem. Of course, X and Y always greater than or equal to 0. I hope you understand now how to formulate the problem and change it from word problem to linear programming problem. Thank you very much and have a nice time.